Have you ever wondered how a black hole forms, how it dies, or what stages it goes through after being created? Because I have, obsessively. But here's the thing, this question is truly one of the most mind-bending questions in all of science. Black holes aren't just terrifying, light-swallowing monsters sitting in space doing nothing. They are born, they grow, they change. And this is the part that fascinates me the most. Black holes die. The universe may be filled with the remnants of ancient black holes that quietly faded out of existence billions of years ago. Wild, right? Today, we're going to explore the entire life cycle of a black hole in 5 stages. From the moment a star runs out of fuel and the countdown begins, all the way to the final evaporation, that slow, almost ghostly fade into nothingness. And I promise you, by the end of this video, you'll look up at the night sky differently. Not with fear, but with awe. Because what's happening out there in the depths of space is far stranger and far more beautiful than anything you could ever see in a movie. If this video gets 20,000 likes, I'll do a face reveal. Alright, let's begin. Stage 1 is where everything begins. And it starts not with a black hole, but with a star. But not an ordinary star, a truly massive star. Now, I want you to imagine a star, but not our sun, because our sun is actually pretty average. I'm talking about a giant star. A star with 20, 30, or even 100 times the mass of the sun. These are called OB stars, or massive stars, and they live fast and die hard. They're basically the rock stars of the cosmos. Let's look at what's happening inside these giant stars. At the core, there is a constant nuclear fusion reaction taking place. Hydrogen atoms are merging to form helium, and this process releases an incredible amount of energy. The outward pressure created by fusion prevents the star from collapsing under its own gravity. In other words, there is a perfect tug of war between gravity pulling inward and nuclear pressure pushing outward. But here's the truth about fuel. Eventually, it runs out. And when a massive star starts losing its hydrogen, it begins fusing heavier elements. First helium, then carbon, then oxygen, then silicon, until finally it reaches iron. And iron is where everything starts to go wrong, because fusing iron doesn't release energy, it absorbs it instead. So the moment a massive star builds up an iron core, that tug of war I mentioned comes to an end. Gravity wins. Instantly. The core collapses in less than a second. We're talking about a tiny fraction of a second. And the outer layers of the star begin crashing inward at an unbelievable speed of around 70,000 kilometers per second. What happens next is one of the most violent events in the universe, a supernova. The rebounding shockwave tears the outer layers of the star apart in an explosion so bright that it can outshine an entire galaxy. For a brief moment, a single dying star can emit more light than 200 billion stars combined. Think about that, 200 billion stars. But here's the interesting part. What remains at the center after all that chaos? If the original star was between about 8 and 20 solar masses, what remains is a neutron star, an incredibly dense sphere of neutrons about the size of a city. But if the star was even bigger, if the collapsing core is more than about 3 solar masses, the collapse doesn't stop at a neutron star. Gravity keeps winning. The core collapses beyond every known physical limit and eventually becomes a singularity, a single point of infinite density. And surrounding it, a boundary forms where the escape velocity equals the speed of light. The event horizon, a black hole is born. Now I know terms like singularity and infinite density sound like pure physics jargon, so let me give you an analogy. Think about the entire mass of the sun, roughly 2 million trillion kilograms. Now imagine compressing all of that into a sphere only about 6 kilometers wide. That's roughly what happens inside the core of a massive star. The density becomes so extreme that the laws of physics as we know them literally break down. We don't have equations capable of describing what happens inside. Albert Einstein's theory of general relativity breaks down here. Quantum mechanics breaks down too. It's as if the universe hits a wall, and that wall is the singularity. Now, and this absolutely blew my mind when I first learned it, the black hole itself doesn't actually look like anything at first. There isn't some giant dark sphere just sitting there. The event horizon is invisible. It's simply a boundary in space. Right after a supernova, there's so much hot gas and debris flying around that even if you were nearby, you wouldn't be able to see it clearly. And for billions of years to come, the universe will continue to change around it. So the black hole exists now. Stage 1 is done. But a newborn black hole sitting alone in space is just hanging out. Gravity is doing its thing, but there's nothing nearby to consume yet. At least not right away. This changes. And this is stage 2, the feeding phase. Here's the thing about black holes that I feel like movies get wrong. They're not the these cosmic vacuum cleaners that immediately start sucking everything in. If you replaced our sun with a black hole of the same mass, not bigger, Earth would just keep orbiting it like normal. The gravity would be identical. We'd freeze to death from the lack of sunlight, obviously, but we wouldn't get sucked in. Black holes are only dangerous when you get close to them, but here's where it gets interesting. In the universe, things are always moving. Stars drift, clouds of gas shift, binary systems form where two objects orbit each other, and when a companion star or a gas cloud wanders too close to a black hole, that's when the feeding starts. Matter begins to spiral inward, and as it spirals, something incredible happens. All that infalling gas and material doesn't just drop straight in, it forms what's called an accretion disk. Picture water spiraling down a drain but scaled up to light years. As the gas spirals in tighter and tighter, it compresses and heats up. We're talking temperatures of millions of degrees Celsius. The disk glows, it radiates, it blasts out X-rays, ultraviolet light, all kinds of radiation. And this is actually how we find black holes. Not by seeing them, but by seeing the insane light show going on around them. Some of the most luminous objects in the universe are called quasars, and they're essentially supermassive black holes in a feeding frenzy. The accretion disk around an active, supermassive black hole can outshine its entire host galaxy by a factor of hundreds. Trillions of stars worth of energy being pumped out, all because of matter falling toward a black hole. And then there are relativistic jets. Some black holes, especially the actively feeding ones, shoot out these enormous columns of superheated plasma from their magnetic poles at nearly the speed of light. These jets can stretch for hundreds of thousands of light years, like cosmic fire hoses. If one of those jets were pointed at Earth from a few thousand light years away, it would sterilize our planet. Just game over for DNA. Now, there's a question I used to think about a lot, especially during this phase of a black hole's life. What happens if you fell in? I know this sounds morbid, but stick with me, because the answer is genuinely one of the most philosophically bizarre things in all of physics. If you fell toward a black hole feet first, the gravitational pull on your feet would be significantly stronger than on your head because your feet are closer to the singularity. This difference in gravitational force across your body is called tidal force, and for a stellar mass black hole, one of the smaller ones, this tidal force near the event horizon would stretch you out vertically and squeeze you horizontally. Scientists literally call this process spaghettification. You would be stretched like a noodle. That's a real scientific term. We name the process of being torn apart by a black hole after pasta. I love this field, but here's the twist. For a supermassive black hole, one that's billions of solar masses, the tidal forces near the event horizon are actually much weaker. The event horizon is so far from the singularity that the difference in gravity across your body would be almost unnoticeable. You could cross the event horizon of a supermassive black hole without even feeling it. You wouldn't know you'd crossed the point of no return until much later.